Hello, welcome to my channel. Today we're going to implement logarithmic function using operational amplifier, where the output voltage of the circuit is directly proportional to the log of the input voltage. So we take an op-amp and ground the non-inverting terminal of the op-amp. The schematic is very similar to an inverting amplifier, where the only difference is the resistor at the feedback is simply replaced with a simple diode. We will analyze through the circuit and derive a relationship between V0 and Vin. One of the most important characteristics of the op-amp is that the input terminal have very high input impedance. That means no current will flow through this portion of the circuit. There will be no current through the going to the input terminals. That means the entire current that is flowing through this path will eventually reach this path, will be eventually passing through this path. That means IR, the current through the resistor, will be equals to the diode current ID. We can find IR through Ohm's law, basic Ohm's law. V in minus V2 divided by R. Another characteristics of op-amp is that V1 is equals to V2. That means voltage in this portion and this portion is same. Since V1 is equals to 0, because it is connected to ground, V2 will also be equals to 0. That means V in divided by R is equals to IR. We have found IR, we need to find ID. For ID, we will use the Shockley equation of the diode. So ID is equals to IS e raised to VD by N VT minus 1. This is the diode equation where ID is the diode current, VD is the diode voltage, IS is the saturation current, N is the identifying factor, and VT is the thermal voltage. N is 1 or 2. For silicon it's 1. For VT is the thermal voltage, which is approximately 26 millivolts. We can approximate the diode current to be by ignoring the 1. That now we have found the ID and we have found IR. Using this relationship, we can now equate both of them. That means V in divided by R is equals to IS. We can log on both sides. At first we can take IS to the other side. We can say mathematically ln e raised to x is basically x ln e, where ln e is 1. So we can use the same principle here. Ln v in by ris is equals to vd by n vt, where vd is equals to the negative of v0, so we replace vd with v0. Ln we take this to the other side. V0 is equals to minus vt ln v. This is our final equation. To write this clearly, v0 is equals to negative of n vt ln v in by ris. RIS, N and VT are all constant. Therefore, V0 is equals to K ln V in. Therefore, V0 is directly proportional to ln of V in. This is the relationship, hence established. After implementing the circuit on a simulation program and applying a bunch of input voltages, we received the following output voltages. If we analyze our results table, we can clearly see that our values represent the behavior of the logarithmic function. For example, if we increase our input voltage by 10 times, our output voltage changes by a constant amount. 534 minus 432 is 102 millivolts, which is approximately equals to 100 millivolts, which got added. Again, if we multiply our input by 10, from 10 to 100, our output voltage will be 635 minus 534, which is 101 millivolt, which is approximately again 100 millivolts. That means every time we are increasing our input voltage by 10 times, our output voltage is getting added 100 millivolt. Now how does this represent the logarithmic relationship? Take your calculator, look for ln1. ln1 is 0. Increase the input 10 times, which is ln 10 is 2.3. ln 100 is 4.6. ln 1000 is 6.9. So every time we increase the input by 10 times, our value increases by plus 2.3. So on the input side, we increase by 10. With 10 times it, on the output, we have an addition of 2.3. So the input side is multiplication, the output side is addition. So that's it for today's video. Thank you for watching.